Good evening, everyone. My name is Raghu. I'm an early career fellow here at the college, and I'll be chairing today's seminar. So it's my pleasure to introduce David Lucas, who over the past 20 years or so has built one of the world's leading trapped ion groups. I won't list all of the achievements, but recent ones include the first demonstration of an algorithm across two separate quantum processors linked by a quantum network, and the world's highest fidelity quantum operation, with errors of about 1 in 10 million. Unfortunately for Balliol College, these achievements, amongst others, have led him to be appointed as a Hooke Chair in Experimental Physics, which means that he'll be leaving us, but not before giving this talk. And just before I hand it over to David, I'd just like to remind the audience that if you have any questions, just feel free to type it into the Q&A box, and we'll get to them after the talk. All right, I'll hand it over to you now, David.
Thanks very much, Raghu, for that very kind introduction. I hope my camera's on okay. Do shout if it's not. So I guess the first thing to say after Raghu's introduction is that it is true that we've had some great successes in our research group in Oxford, the group that Raghu and I are both part of, and those a lot of those successes depend, of course, on teamwork. People like Raghu and my younger colleagues and students. Many of the PhD students I've supervised have been at Balliol over the last 20 years where I've been there. So I can't take credit for the work all myself. Now, I'm here to talk to you about codes, computers, and quantum physics. And the Development Office has circulated a brief summary of what I'll be talking about. And I'm mostly going to be talking about the background to the work that we do in the physics department in Oxford. And I'm going to start with a little bit of a background about conventional computing, or as it's often called in our area of physics, classical computing. So classical as opposed to quantum computing. I'll talk a little bit about cryptography, as that's one of the important applications of quantum computers if we are ever successful at making them. And I'll go back and talk about the basics of quantum physics, really, what it is, what are quantum systems, why is it important, why is it different, why does it allow us to compute in a different way. So I'll talk a bit about atoms and electrons, which are the sort of size scales of matter where quantum effects start to become important. And a very important part of quantum mechanics or phenomenon in quantum mechanics is called superposition. And that's one way of illustrating how or why it is that computing with quantum bits instead of conventional or classical bits can be more powerful. And then I'll just finish up the last few minutes by introducing you to real qubits, or as quantum bits are called for short, qubits, the kind of qubits that we use in the lab in the experiments that Raghu and I and others do. And if I have time, briefly talk about where the sort of rough state of the art of the field is at the moment. Okay, so you probably, I guess if you're here for the talk, you probably have some interest in quantum computing. You may have heard about it before. It's certainly become a lot more in the public consciousness in the last 5 or 10 years, when a lot of countries around the world have started quantum technology programs, and one bit of quantum technology is quantum computing. But it's actually been around as a theoretical idea for around about 40 years now, and people have been doing experiments in the field of quantum computing in experimental physics labs for perhaps nearly 30 years. So it's almost getting to kind of a venerable age field. And of course, people always ask, when are we going to have quantum computers? When are the real things going to be here? This idea has been around for ages. Is it ever going to happen? And I always like to remind myself that the classical or conventional computing, the computers that we're so familiar with, that are our laptops and in our phones and everything, also have a long history. And it was a long time from the theoretical ideas to the real thing, and even longer to the the sort of devices that we have today. So really the history of the idea and theory, perhaps for a general purpose computer that could we would recognize today as a generalized information processor, as opposed to just a calculator that can do, adding up numbers, something that can really process information, do logic, and make decisions. And so I'll go back to Charles Babbage, a mathematician in the 19th century, and Ada Lovelace is often given credit as one of the first people to sort of understand how his machine worked and program it, or actually come up with programs. Now, Babbage could never get his machine to work, partly because it was ahead of the ideas were ahead of the technology of the time, perhaps a little bit like quantum computing now. And it wasn't until the 1930s, perhaps, that we had real mechanical computers that could actually solve mathematical problems and differential equations and so on. Konrad Zuse in Germany was one of the pioneers of those sort of machines, perhaps the first, again, sort of generalized programmable working mechanical computers, which he started out building on his parents' kitchen table in Berlin. Then the spur of the Second World War, of course, really pushed forward the development of computers, and that's when electronic computers came along based on valves. So valves were it's an electronic amplifier essentially, but that is a key part of representing a single bit of information in a machine, but they're large and unwieldy and unreliable electronic devices. Alan Turing was, of course, the well-known person who designed a lot of these machines. Tommy Flowers was an electrical engineer who built the first electronic computer, Colossus, which was, again, a sort of programmable electronic computer dedicated to code breaking at Bletchley Park in those days. But it wasn't really until the invention of the transistor that was really the key device which enabled computers to turn from sort of large, very, very specialized, extremely unreliable machines into things that could be scaled. And there's really a direct line from the invention of the transistor at Bell Labs in the US in the 1940s to the sort of silicon integrated circuits that we use today. And there's been, that's really when the development took off. And Moore's law, of course, is very famous. One way of illustrating that is the number of transistors that are packed onto one silicon chip, and how that increases in an exponential fashion. So this is a graph here on logarithmic scales, showing here both how the feature size of the transistors and other electronic components on the chip gets smaller and smaller over time, and the number of transistors gets larger and larger over time, which is all very well and explains the incredible advance in processing power of computers over the last decades. But of course, this scaling can't go on forever. I mean, this feature size here can't get smaller than the size of a single atom, for example. So that's one limitation on scaling the devices that we use today. And of course, when you get down to size scales of single atoms, that's when quantum effects become important. Okay, so that's supposed to be a brief history of classical computing. As I mentioned, one of the key reasons and drivers of classical computing was the, let me just put on my points here, was the need for code breaking machines in the Second World War. So let's take a little bit of a digression into cryptography. So here's a secret message up here, and here's the decoded message underneath. Okay, my message is a very simple one: let there be light. And how have I encoded it? Well, I've just taken every letter of the message and replaced it by a different letter in the alphabet according to this key down here. Okay, so where my plain text letter is an L, I code that as a Q. So that's the first letter there. And where my plain text was an E, I've encoded that as a J, and so on. So very simple substitution cipher, as it's called. And this famously dates back to the days of Julius Caesar and others, where this was apparently for centuries a perfectly good and secure way of encoding messages. Rather surprisingly, as it's not that difficult, particularly if you've got a long message, to figure out what the words might be. If you know what language it's written in and so on. For example, in English, E is the most common letter, and so you do a frequency analysis on the encoded message. It's not too difficult to break. But I suppose in the days when many people couldn't even read and write, let alone break codes or do mathematics, then that was a secure method. As I say, that seemed to persist for centuries until sometime in the 1600s. French mathematician Vigenère improved it by saying, well, what about instead of always using the same alphabet here, where this alphabet, as you can see, is just shifted along by 5 places compared with the original one. Instead of doing that, let's have 26 possible different shifts of my alphabet. So each row of this table here then just represents one possible encoding. Okay, where before I was using the alphabet that was down here, the 6th row of here that started with F. Okay, that's what I was using there. Now, so the advance of the idea here is that, well, instead of always encoding the letter E, for example, as Q, as I was doing before, J, as I was doing before, we swap between different alphabets. And the way we swap between the alphabets is given by using a keyword up here. So there's my message at the top again, let there be light. I've chosen a very simple 3-letter keyword, lux, happens to be Latin for light, as my keyword, and I just cycle through these 3 different alphabets here labeled by L, U, and X on the left. Okay, so when I choose the alphabet beginning with L, I then encode the letter I want to encode, which is also L. In my example here, I go down that column from L, and that turns into W. Okay, so that's why my coded message has a W. And then, but if I look along here, look, here's another L, which I'm encoding, but I'm encoding that using the code alphabet beginning with U. Okay, so L encoded with this alphabet down here, this row of the table encodes to an F. So the same letter is not always encoded as the same letter. Same letter in the plain text is not always encoded in the same letter in the encoded message. So that's obviously a lot more secure. Having said that, turns out you can still break this code because it still has some structure in it. Okay, because I'm cycling through here in my simple example with a very short code word, only 3 different alphabets, I can still do a more clever version of the frequency analysis method and break this because the encoding or the keyword has a simple structure and a repetition. And interestingly, the guy who worked out how to break this code first was the very same Charles Babbage, who came up with some of the first ideas of computing. So the only way to make my encoding, this sort of method, completely secure is to have a longer and longer keyword. In fact, a keyword that is as long as my message. If you think about it, provided the keyword does not repeat, and if the keyword is just, for example, a random string of letters itself, then there's absolutely no way, if you think about it, I can get any information by analyzing the encoded message without having that keyword. And essentially, that was the basis of more advanced encryption methods, which, when mechanical machines came along to encrypt messages, enabled so-called perfect security. And a famous example of that is the Enigma machine from World War II. Now, of course, it wasn't actually perfect because there was still a keyword, but it was kept carefully secret. And the way the message was encoded was some very complicated function of how that keyword works. So that was fine in terms of practical security, because if you didn't know the keyword, then there were millions, if not trillions, of combinations one would have to try to decode the message, essentially by brute force and trial and error, even when you know how the machine works and how it's internally wired up. And that was why the machine was regarded as essentially unbreakable. But in reality, and famously, of course, the Bletchley Park crew, not far away from Oxford, worked out how to, with knowledge of how the machine was built and how the different possibilities worked out, essentially brute force methods of cracking the codes by developing machines like the Colossus computer that could cycle through millions and millions of trial and error attempts until sensible messages came out. That's one of the rare photos of the original machine, which survived because not only was the machine itself, but all the drawings and designs of the machine were intentionally destroyed at the end of the Second World War. Very incredibly, in light of that, a bunch of volunteers in the 1990s managed to reconstruct the machine from photos such as this and from the memories of the people who had built it and were still alive and around. And this is actually a working version of the Colossus machine, which is very impressive if you ever visit Bletchley Park, which is now a museum, and the National Computer Museum in the UK. Okay, so what's that got to do with our story? This was all very well, but these kind of code systems, such as the Enigma machine, have a crucial practical limitation, which is that one has to distribute the keywords. So remember, essentially, we're still using a more complicated version of this system where we need to know the keyword to know how the message is encoded. Once we know the keyword with our machine, if we have the right machine, we can decode it. But that means the sender and receiver both need to know the keyword, and it has, of course, to be kept secret. So that's a big practical limitation because it means you have to distribute to every unit of your army in wartime, for example, a code book. And if one single copy of that code book falls into enemy hands, the entire communication system is compromised, and you've got to distribute a brand new code book, and you've got to get that to every unit of your military. This is clearly an extremely difficult challenge, and it only takes, as I say, one code book to fall into enemy hands, or one courier to lose his code book, or to be bribed, or whatever, to give up the codes. So this idea of distributing the key is an incredibly important practical limitation on making codes. And one would seemingly think, well, the only way we can have security between two people, often called Alice and Bob, is that Alice and Bob have to share some bit of secret information. Interestingly, turns out that is not the case. And an invention that was made in the 1960s, 1970s was the idea of public key cryptography. And this is the idea where instead of having a secret key that Alice and Bob have to share between them, Alice can publish a sort of half of her key, which is the public part of it, and anyone can use that public key to encode a message, but Alice keeps the other half of the key, which is a private half, and in order to decode the message, you need that private key. And this sounds, when you first come across the idea, like it's impossible, but there's a nice analogy to this, which maybe makes it seem a little bit more plausible, which is that imagine that Alice puts her message, whatever it was she wants to send to Bob, in a box, and she puts a padlock on that box, locked with her own private key. She sends the box to Bob, and Bob cannot take the padlock off because he doesn't have Alice's key. Instead of doing that, he puts his own padlock on the box in addition to Alice's, and locks that with his own key, which is different to Alice's key, of course. He sends the box back to Alice. She takes her padlock off. Finally, she sends the box back to Bob, and he can take his own padlock off, which is still there, and get access to the secret message inside. So there's a way there where they have not had to exchange the key to the padlock, because they only have their own private parts to it. So that's an analogy of how this idea of public key cryptography works, and it's immensely important, not just for military applications, but you and I use this every day on the internet. If we want to buy something with a credit card and not reveal those details, it relies on a system of public key cryptography. And what it relies on at heart is a mathematical operation that is easy to do in one direction, but difficult to do in the other direction. And here's a simple example of that, which is that if I give you a 5-digit number, like here, 24,287, I tell you that this is that number can be obtained in only one way, by multiplying two numbers together. So that means the two numbers are multiplying together, by the way, have to be prime numbers. But as I say, it's relatively difficult to find what those two numbers are. As I said, there's only one possible answer to this, apart from trivial ones like 1 times 24,287. Apart from that, so it's relatively hard to find the factors of that number and to factorize. But going the other way, if I tell you what the answers are, they're 149 and 163, it's relatively easy. And we can probably all of us still remember how to do that with long multiplication. Might have to scratch our heads a bit to remember the exact methods of doing that, but it's not a difficult operation. Whereas it turns out going the other way, so multiplying is relatively easy, and factorizing, which is going the other direction, is relatively hard. And it's not just hard for human beings, it's hard for computers as well. It turns out there's no better way than just doing it by trial and error. So of course, a fast computer is not going to take very long to factorize a 5-digit number, but if you make the number long enough, it does take a very long time. And the reason it takes a long time is it doesn't just get a little bit more difficult when you add another digit to the number. It gets more like 10 times more difficult. And one can get an idea of that because of the obviously the number is 10 times bigger, and there's many more possibilities that we tried. So it's a problem that scales up rapidly, and by the time you get to something like 10, 20, 50-digit numbers, even the biggest supercomputers around can't factorize them. That is at the heart of this method of public key cryptography, and as I say, that's what we all rely on at the moment. And one of the reasons that people got so excited about the ideas of quantum computers when they were first proposed, as I say, back in the 1980s, was that it turns out that one of the things they could be good at is exactly this operation of factorizing rapidly. And therefore, they would be a potential threat to the sort of public key cryptography that we all use every day. So particularly, for example, people in national security agencies and so on got to, and intelligence agencies started getting very interested in these ideas. Okay, so so much for our digression into cryptography, code making, and code breaking. What I said I wanted to talk about next is to switch back to the theme of quantum physics or quantum mechanics, and tell you a little bit about basic quantum systems like atoms and electrons. And then I'll come back and show how that is related to the computing side of what we're talking about. So, as I mentioned right at the top, quantum mechanics is the area of physics which describes small objects. And if I want to be quantitative about small, I mean roughly the size of atoms or smaller, and atoms are about 1/10 of a nanometer in size. Okay, about 10 to the power minus 10 meters. A nanometer is itself 1/1,000,000th of a millimeter. Okay, so extremely small objects compared to everyday sizes. And that is about as I say, the size scale where it becomes impossible to understand the world properly without quantum mechanics. Now, there's people trying to understand how atoms worked using the well-known laws of Newtonian mechanics, or classical mechanics, as physicists call it. And those models failed to explain adequately how atoms worked, and in particular, the structure of atoms. So, I'm going to look at an atom. I'm going to show you a picture which is from one of our labs, which is a pretty famous photo now, as it's been all out there on the internet. And it was taken by David Nadlinger, who was one of my DPhil students, and he was in fact at Balliol. And he took this wonderful photo, won a national science photography competition with it a few years back. And depending on the quality of your screen and what you're looking at here, if you look very, very closely at the center here, you will see just where I'm circling my laser pointer around, one single bright dot, about the size of a pixel on my screen. That one single dot is one single atom. Okay, one of these incredibly small objects, localized and held in space. And it's held in space by this metallic device around it called an ion trap. And these bits of metal here are nothing very exotic. They're just electrodes machined out of stainless steel. And you can see nuts and bolts holding this thing together. And here's a scale bar down here, 2 millimeters. So these nuts and bolts over here are millimeter size scale. So these are, the sort of size of Meccano nuts and bolts that people of my era might have played with as children. And you can see in this one photo, it's not a combination, it's not a superposition of two photos. In this one photo, David has captured the classical world, the macroscopic world of nuts and bolts, and the quantum world of a single atom. The atom, by the way, appears much larger than it actually is. It's limited more like by the size of the pixels in the photo, the camera that David used to photograph it. Now, it's held there by electric fields. It's actually a charged atom, an ion. Happens to be an ion of strontium. We use strontium because if you take one electron off strontium, it has a single electron in its outer shell, its valence shell. So it has a relatively simple atomic structure, a bit like the hydrogen atom. Hydrogen is the simplest atom of all. And the reason you can see that strontium ion there is because it's sitting in a laser beam. And because it's charged, we can hold it still with electric field. So the role of these metal electrodes around here is to act like a cage. They have a voltage on them of a few volts, which provide an electric field which can trap the charged ion in space. As I say, the reason you can see it is because there's a laser beam threaded through in between the electrodes here. And you can't see the laser beam itself because there is literally nothing there for the laser beam to scatter off, except that one single ion. So this is all taking place inside an extremely high vacuum system, about the best vacuum you can conveniently get this side of Alpha Centauri. And the laser beam hits the atom absorbs some of the photons in that laser beam, photons of light, and then scatters them again in all directions. And it's essentially like looking at a very, very faint star, but it's right there in the lab. And David used a good camera to get this, but not a special scientific camera, just a good camera with a good lens and a long 30-second exposure time to capture the very faint light of the atom. And this sort of purpley light you can see scattered around a few places. That's little bits of the laser beam, which are just stray reflections catching on things and bouncing into the lens of the camera. So as I say, lovely photo which captures the quantum and the classical world. And this is our starting point for a lot of our experiments on using atoms or these single ions as quantum bits for quantum computers. But just going back to atoms and how they work, why did we need quantum mechanics to understand atoms? Well, if you look at the light emitted by atoms, and if we go back to the simplest atom, hydrogen, you look at that light, it consists of different wavelengths. Okay, but it's not like white light. White light is made up of all the colors of the spectrum. The different colors you get out of a particular atom are very characteristic of that particular atom. There its fingerprints. Hydrogen, for example, if you look at it and split the light up into its constituent colors with a diffraction grating or a prism, you'll see these different colors. You'll see a strong red line here, and the wavelength of that light is in nanometers here, 656 nanometers, and you'll see a blue line here and deep purple lines going off here towards the violet end of the spectrum. And these lines have a particular spacing here, and this was observed. Of course, you don't need to control to have single atoms to see this. Hydrogen's all around us. It's particularly in stars around in the universe and so on. But you can perfectly well get a sample of hydrogen in the lab and get it to emit light like this. And there may be billions of atoms in there. It's not really any more complicated than a fluorescent lamp. And people discovered this, and then they looked at different atoms and they found different sort of colors. For example, sodium has a very characteristic orange color, which is in old-fashioned street lamps before they were replaced by LED lamps. And the different flame tests that one learns about in chemistry for different elements, again, tell you about the characteristic colors that are emitted. So to explain the fact that these colors occur at these very precise different wavelengths required something beyond traditional, conventional, classical, Newtonian physics. It required, it turns out, quantum physics. And really the fact that we see certain particular colors of light here reflects the fact that atoms can only exist with certain allowed energy levels. Or if you want to think about an atom as a miniature solar system, if your picture of a hydrogen atom might be the nucleus, a proton with an electron circling around in some sort of orbit, only certain orbits are allowed in the atom. That's very, very different to putting a planet in orbit around the sun or a star, where that planet can in principle be in pretty much any orbit. Only certain orbits are allowed for electrons in atoms. And when the electron jumps between one orbit and another, it's the atom changing energy. The difference in energy is emitted as a single particle of light, a photon of light, of a precise color. So the color of the light determines the energy of the photon. So, as I say, it required the development of quantum mechanics to explain the atomic world and indeed the subatomic world after that, when people started probing inside the nuclei of atoms. But a lot of the early developers of quantum mechanics, and 2025 is the year of quantum, by the way, because it's marks 100 years since the development of the sort of proper theory of quantum mechanics by Schrödinger and Heisenberg and others. And the theory of quantum mechanics is incredibly successful. It explains not only the colors of light emitted by atoms and their structure, but every single test that we've thrown at the theory of quantum mechanics, it passes, even though a lot of those originators, the original developers of quantum mechanics, were very unhappy about some of the implications of the mathematical theory. So Albert Einstein famously said, God does not play dice. What does he mean by that? It's because it turns out that at the heart of quantum mechanics is probability and chance. And in a way that's qualitatively different to the chance and probability you get when you toss a coin or throw a dice, which can give us a random number. But if I knew exactly what speed I threw the dice at and how much it was rotating, I could predict exactly what number was going to come on the dice, or likewise when I toss the coin. There's a different sort of randomness in quantum mechanics, that the theory says that you can know every possible thing. It's possible to know about the system that you're looking at, and you can't necessarily predict the outcome of a given measurement you make. So a good way of illustrating this is often we talk about this when we're introducing quantum mechanics to our students, is via a thought experiment, or real experiment as well, one can do, but an experiment called the two-slit experiment. And this illustrates the sort of wave, this wave particle duality, which is also part of the strange predictions of quantum mechanics. So let's forget about atoms and so on for a moment, but and just imagine we have waves, and these could be water waves or sound waves, and the waves are coming along, they're hitting a barrier here. So this is a sort of bird's eye view. I've got a barrier here, and it's got two little gaps in it, or two slits. Okay, so we just imagine that barrier completely absorbs the waves, unless the wave goes through the slit. Okay, so if you do this experiment with water waves, what you see is the waves go through, but where they come through a slit like this, if the size of the slit is similar to the wavelength of the waves, and these red lines here just represent like the crests of each wave, okay, then the wavefront curves around like this, okay, and the waves spread out. So this happens all the time. I mean, this is the reason with sound waves, for example, you can hear things around the corner of a building, is because the sound wave comes around that corner and diffracts around. Diffraction is the technical name for this. If that happens with these two slits, you get these two sort of curved patterns of waves that come out, and you can imagine this with, I hope, with water waves. And what you see here is where the crests of the waves of the two different wave patterns overlap, then they add up. So you get a wave which has a crest which is twice the height. And in between the crests are troughs. And if I put my pointer here, that would be troughs of both wave patterns from the top slit and the bottom slit overlapping, and I get a deeper trough. Conversely, if I have a crest here on top of a trough, a crest from one wave intersecting with the trough of another wave, they cancel out. Okay, and so at that point, the water, if there's a water, would be precisely still and it wouldn't be going up and down. Okay, so if I look at this with a way of observing the waves over here, and if I now do this with light, and these are light waves, what you see over here on the screen is where at the points where, like here, the crests meet together, I will get bright light, and at the points where a crest and a trough coincide, I will get dark bands of light. So I get something like this. Okay, so I get a bright fringe in the middle, and then a dark one, and then a bright one. Okay, and this is a perfectly static picture, even though the waves are bouncing up and down. And this is called an interference pattern of my two waves. Okay, so nothing too mysterious about this. As I say, this happens with all kinds of waves, water waves, and sound waves, and so on. Now, the interesting thing is what happens when you do this with particles. Okay, again, if I just imagined throwing tennis balls or something at this system here, of course, the tennis ball would basically go through the slit, or it would rebound off back here. But if it went through, it would just come through and land in two different places. So if I were to think about doing this same experiment with tennis balls rather than waves, I would get a very different behavior. Okay, tennis balls will always end up in one place. I wouldn't get this sort of spreading out of the tennis balls. That would be crazy, right? However, when I do this experiment with small enough particles like atoms or electrons, something rather interesting happens. So electrons, which we generally think of as particles, I pass them through the double slit here, and over here I have some sort of screen for detecting electrons, and I will see the same sort of interference pattern, bands of light and dark here, as I get with light. So we might say, oh, well, in that case, maybe I was wrong to think the electrons are particles and they're actually light after all. But if you do the experiment more slowly, so I fire individual electrons through here at a time, this is now a picture of what I would see on the observing screen, and this is a real experiment that somebody's done, and I see little dots here, which is the points on my detector here, which is like a camera, of where the electrons have arrived. And they definitely seem to have arrived as little points, as I imagine would happen for little particles. Okay, so I run my experiment for a while with a few electrons going through, and I get a few dots like this. If I do it for a bit longer, I get a few more, and this just looks like sort of random speckle on here. But if I do it for long enough, a bit longer, and a bit longer, and a bit longer, you'll see now that all these dots add up to give us this same interference pattern that is characteristic of waves. Okay, so this is, as I say, illustrating this wave particle duality. When I do it, each individual electron fired from my gun, and the experiment here is done slow enough so that there's only one electron in the apparatus at a time, arrives as a click and a lump or a quantum. But after a while, a pattern builds up out of all these little clicks and lumps, out of millions and millions of them, that looks like what I get for water waves or sound waves. So somehow my electrons have characteristics of both. So again, if I were doing this experiment with particles, I expect them to end up in just one place, and somehow when I do this with electrons, they end up in this sort of interference pattern over here, and that's what it would look like. And in a sense, the whole sort of mystery of quantum mechanics is to say, well, actually, what is going on here in between this part here where I've got electrons which I'm sending in, and here I've got electrons which I'm sending out. In here looks like some kind of wave thing. And maybe I'm trivializing things a little bit, but in a sense, we just don't know, right? In a sense, it's very difficult to know what's going on. There's a mathematical theory of quantum mechanics which tells you, well, yes, there's the wave interaction is going on here, and somehow these things are behaving like particles out here, and over here when I measure them, if I try, the really mysterious thing, I suppose, is if I try and measure, I put a little detector by this slit and a detector by that slit and try and measure which way the electrons are going, they turn back into behaving like particles. Okay, and I can't do anything to measure them without somehow destroying the wave characteristic of the nature. So all this is a little strange, and the sort of reason, if you like, or the way this is described in the mathematical theory of quantum mechanics, is that if I put just a single electron through this apparatus at a time, it somehow goes both ways at once. So even though the electron is, as far as we know, a point particle and an indivisible particle, somehow it knows that there are two slits here and it behaves like a wave. And as I say, even if it's on its own in the apparatus at one time, and a mathematical sort of description of this says that, well, the electron has followed both possible routes through the top slit and the bottom slit, and it's somehow in a combination or a superposition of both these paths at the same time. So this idea of superposition and quantum systems somehow being in two states at the same time, famously illustrated by Schrodinger's cat in a box. This is something that's really at the heart of quantum mechanics. And we can get a sort of idea of why quantum bits are more powerful than classical bits for computing by thinking about superpositions. So let me come back to basics, as it were, or traditional conventional computers, and how conventional computers do arithmetic. Okay, so let's have a quick tutorial in binary arithmetic. If it's not something you've come across before, I'm sure you are familiar with the idea that computers store numbers in binary. It's very convenient in an electronic circuit. We just need two digits for binary number system, 0 and 1. And that's very conveniently represented by, say, two different voltages in an electronic circuit. Okay, so the number 5, for example, in decimal is written as 0101 in binary. Okay, and that's it's a 4-digit binary number, or in computing that might be called a 4-bit register. And why is it 0101? Well, each binary, reading from the right, each binary digit has a place value or a column value. Instead of units, tens and hundreds and thousands, the place value is powers of 2. So it's 1, 2, 4, 8. Okay, so 5 is made up of 1, 4 and 1, 1. Okay, so that's our 4-bit register. Okay, so let me take two numbers, 5 and 3, add them together. Of course, I know the answer is 8, but if I do this by long addition in binary, I write my two numbers here. 5 is 0101, 3 is 0011, and I go down the columns and add. So 1 plus 1 is 2. Well, that's a problem because there's no digit 2 in binary. So I have to write that as 10. So you write 2. And so I carry a 1 over into the 2's column, and I have a 0 left behind. And then I add the next digit. 0 plus 1 is 1, plus the carry 1 from before gives me 2 again, which so I carry 1. Put 0. So there we are. If I follow that rule, I end up with a number 1000, which is, looking at the place value, is 8, as I'd expect. Okay, so that's how you add things together in binary. How do computers actually do that? Well, you implement the logical operations that give rise from the input numbers A and B, or each digit. You want the logical operations which give rise to the sum and carry output. So you write down all possibilities here. There's only 4 possibilities for 2 digits, 2 binary digits, 2 bits, 0001, 1011. And these are the different outputs I get for the sum bit and the carry bit underneath. Okay, if they're both 0, I get 0 out. If one of them is 1, then sum is 1. I don't have to carry anything. But if I have 2 1s, then I get a sum and a carry. And this is these two output digits here represented by a logical operation. The carry bit is simply if A and B. So if A and B are both 1, then the carry has to be 1, as you can see from this little truth table, as it's called down here, this table. And the sum is perhaps a more exotic operation you might not have heard of, but it's called exclusive OR, XOR for short. So the sum bit is only 1 if A or B is 1, but not both. Okay, so those are the logic operations. That's the circuit symbol for electronic circuits of what an AND operation looks like, or AND gate as it's called, and that's what an XOR gate looks like. So, if you delved inside a microprocessor chip, you would find it was just filled with thousands and thousands of these gates to do the different logical operations. Of course, information processing is about more than just arithmetic, but everything can be represented by logical operations, every algorithm or program. So a quantum bit is a quantum version of this digit, but instead of being either 0 or 1, a quantum bit or a qubit, and we could take the electron as an example, can be in two possible states. And the big difference is it can be in this superposition state of the two possible states at the same time. So electrons we often think of as, well, they have a property in physics called spin, and one could think of this as just a spinning blob, if you like, but it can spin clockwise or anti-clockwise, and we call that spin up and spin down. Okay, and we for our computing purposes, we just label those states as 0 and 1, and we'll put this funny sort of bracket around it. It's just how you represent that it's a quantum state rather than a conventional state. And a superposition state could be, for example, written as 0 plus 1. So there's not an adding operation. This is just a way of writing mathematically the fact that the system is in a superposition of those two states. And it's in an equal superposition. So this is just an example superposition. I could have all sorts. I could have, this is an equal amount of each one. I could have sort of 90% of one, 10% of the other, or any superposition I like of those two states. And now, if I have two electrons or two particles, I can have four possible states because I can have them both spin up or both spin down, or one up, one down, or vice versa. And so labeling with a 0 and 1, writing it in my little funny bracket system here, then I can just label it like that. And the convention here then is that the first digit I'm writing is particle A, say, and the second digit is particle B. Okay, so two particles, four possible states. Three particles, well, there's 8 possible states. So this is like binary again, right? I have 3 binary digits, gives me 8 possible states. But again, the difference is with a quantum register of particles, they can be in a superposition of these different possible states. And this is a lot of states, right? When I have n particles, and as you'll see by extending this, I get 2 times 2 times 2 times 2, 2 to the power n states. Okay, and that is, of course, rapidly becomes a very, very large number. So this exponential operation. So every time I add one physical particle, one electron here, one qubit to my system, I double the number of possible states. And as I say, the big difference between a classical register of bits, where I'd also double the number of possible numbers I can store, but in the quantum system, I can somehow be in this superposition state of all possible numbers at the same time. So that gives you perhaps a glimpse of why people get excited about quantum computing. In some sense, the kind of processing power or workspace of the quantum computer grows exponentially with the number of particles I add on. I mean, if I took my laptop, which must have gigabytes and gigabytes of memory in it, so that's billions and billions of bits of memory, and I added one more bit of memory, I absolutely would not notice the difference in performance on my laptop, right? What this exponential thing means is that with a quantum bit, if I have a quantum computer with a certain number of qubits, and I just add one more perfect qubit to that system, I will double its power. Okay, so just think about that for a moment. That is really the source of the power and the interest in quantum computing. Now, there's no such thing as a perfect qubit, so that's the first problem. That's a long story, but it turns out that you can, with sufficient effort, make qubits perfect and correct the inevitable errors that happen in real life. So I'm nearly out of time, so I ought to wrap up here, but I just want to give a glimpse of how we sort of make actual qubits and come back to our single atom. But I should, in fairness, mention that there are all sorts of different technologies people are looking at right now and actively working on, which are alternative ways of making qubits. So here are our atoms or ions. Here's a row or a register of trapped ions. And this is a different kind of ion trap, which looks a little bit more like a kind of microfabricated processor type device. And which can also hold ions, and we can apply electronic signals to these electrodes here, and that can manipulate the state of the ions. And as Raghu mentioned in his introduction, actually, in this kind of trap we've used to do the world's most precise quantum logic operation, just on a single qubit in that sort of demonstration experiment. But one can also do fundamental quantum logic gates, so the equivalent of the and the XOR gate, and things in a quantum system. And in fact, the highest precision one of those operations I'm currently aware of is some work that Raghu has actually been involved in a spin-out company called Oxford Ionics, which came out of our research group. A couple of my former graduate students, one of whom was at Balliol, set up that company about 5 years or so ago. It's already been extremely successful, and that has so together these methods of manipulating our single atom qubits are very attractive. Superconducting circuits is another leading technology. So if you've heard publicity from Google or IBM, for example, they use this sort of technology that perhaps looks superficially, at least, a little bit more like a conventional bit of electronics. It isn't really like anything like conventional electronics. It relies on Josephson junctions, which are electronic components with some very interesting physics occurs at superconducting temperatures of very low temperatures, and here I mean sort of millikelvin temperatures. Here, semiconductor qubits based on, for example, silicon, spins of silicon nuclei and single electrons in a solid state. So people are trying to work very hard on those and benefit from the enormous advanced in fabrication technology that we have for silicon-based devices. Again, quantum devices are really rather different to classical bits, but one can certainly benefit from some of the manufacturing techniques. Diamond is surprisingly another interesting material that can be used. And again, it's single spins, like an electron spin or a nuclear spin, trapped inside the lattice of carbon atoms in a diamond crystal, can also be used. And even individual photons of light, purely photonic quantum computers are proposed, and again, people are working on, and there are large industry companies working on scaling up all these different technologies. It's quite exciting at the moment because nobody really knows which different technology is yet going to win. Just to show a little bit again about our single atom here, say a little bit more about that. In this photo, it was a strontium ion. We also use calcium ions for the same reason. They have a relatively simple structure. And here's a little movie of what happens what it looks like if you zoom in there, and you can see it really is still. It also has a very low effective temperature here, but interestingly, the apparatus here is entirely at room temperature, and it's just a very beautiful technique called laser cooling, which allows us to cool the atoms down right to basically very close to absolute zero. This 0.001 Kelvin means 1 millikelvin, 1,000th of a degree above absolute zero of temperature. Yeah, and the ground state of calcium is it's a single electron system, like a hydrogen atom, and we put on, for example, a magnetic field. There are just two quantum mechanical states here in the ground state of the atom, which can quite conveniently be labeled as our 0 or 1 states, or spin up, spin down. So that's a good example of a quantum bit, and they're trapped in this device schematically here called an ion trap, which where the electrodes here, as I mentioned, have a combination of DC and AC voltages, which can trap the charged ions. And again, here's a photo of real ones trapped in our trap. That was the very first ion trap that we built in Oxford about 20 years or so ago. So I just wanted to finish with a little flavour of the other absolutely crucial thing, which I haven't really had time to explain, which is called quantum entanglement. But quantum superposition, quantum entanglement, these are these uniquely quantum properties that we just don't see in the macroscopic world, and are both crucial to the operation of a quantum computer. So I want to show you what quantum entanglement is with a little video. And again, this is the real thing. What we've got here is two of our ions in one of our ion traps, and we're making this superposition state of our 2 qubits. Remember, there were 4 possible states here. We're making a superposition of the state with both of them, both qubits 0, both qubits 1. And what you can see there is when we're doing that repeatedly, and then we measure the state, quantum mechanics tells us we're going to get one half of this superposition or the other half at random. We don't know which one. This is a bit like my electron going through one slit or the other slit in that Young's slits two-slit experiment. So the first thing you see here is this is a completely random process. I cannot tell you when I measure it whether I'm going to get both these atoms bright or dark. So bright here corresponds to, say, the 1, 1 state, and dark to the 0, 0. The other thing you can see is we can do this pretty reliably. So if you watch carefully, there's one frame in this movie out of about 100 where, there it was, we just went where we had one bright and one dark, and something had gone wrong. And so that's one entangled state one can make. From that entangled state, the other obvious one can make is called 0, 1 plus 1, 0. And by the way, entanglement, it's not just a pretty word. It really goes to the heart of what's going on in the quantum system. It means that the states of these two particles, when they're in one of these entangled states, they really are inextricably linked together. I could make that entangled state. In principle, I could take one of those atoms to the other side of the planet, and I could measure it on the other side of the planet. Somebody else could stay here and measure it here, and the states they would get would still be correlated in the same way as in these experiments where they're right next to each other, just a few microns apart. So I'll wrap up there. As I say, quantum computing has had quite a long history since the early theoretical ideas. Maybe one way to be optimistic about the progress is, of course, to look back at history of our non-quantum computers, or our conventional computers. We are used to having chips like this in our phones or our laptops, an Intel processor with millions and millions of transistors in them. But when one goes back to the early days of computers, the predictions of how powerful computers will be were very different. So this is a famous quotation that 1949, computers in the future may weigh no more than 1.5 tons. Now, of course, I guess the only thing history teaches us is that history doesn't teach us anything, but I think certainly the future of quantum computers, given the progress in the last 5 or 10 years, is pretty exciting. So I will finish there and hand back to Raghu.
Thanks a lot, David, for that fantastic talk. And I really appreciated, I think, the introduction with classical cryptography and computation. Just a reminder to the audience that if you have any questions, you can type them into the Q&A and we'll go through them. Maybe I could start with a question from me. What do you think are the main roadblocks towards a practical quantum computer?
I think they're sort of what they've always been since the beginning, which is you need both more qubits and better qubits. So it's very easy to sort of count, and people often do this when they're looking at the progress of the companies, count how many qubits have they got in their latest device or system or experiment. But actually, you could have an infinite number of qubits, but if they're too poorly controlled, you can never build a quantum computer out of them. So I've got a slightly more technical slide if somebody wants to delve into that, with a graph of that, but to quantify that. But roughly speaking, if you have in each fundamental quantum operation, by which I mean something like doing one of these logic gates, or even just putting the numbers that you want to add together into your qubits, preparing the qubits in the first place. If those operations are not sort of 99.99% reliable, then theory tells us that even if we could build a quantum computer, it would need an awful lot of qubits, millions and millions. And the more reliable one can make those operations, then the fewer qubits one needs to deal with the inevitable errors that will creep in. So I think that's the biggest challenge. As I mentioned, work you've been involved with Raghu at Oxford Ionics has pushed the most difficult operation, which is generating the entangled state. The video I showed there was starting with two non-entangled particles and making them entangled, and that seems to be, whatever quantum system you're looking at, generally the one that's most difficult to do. And I think that's maybe easy to see, that you can find quantum bits and qubits that act as really good qubits because they're really isolated from the world around them and environment. And these quantum, fragile quantum superposition states can last for a long time, minutes in some of our experiments, hours in some systems. But to entangle them together, you somehow got to get them to talk to each other, and to do that, somehow you've got to come out into the real world from however pristine your qubit is, and the real world is sort of noisy place at the atomic scale. So it seems to be a general rule that the entangling operation is a very difficult one to do. So,
All right, great. Thank you. All right, so moving to some of the audience questions. So we have a question here from Adrian. Could you comment on what you think of the modular ion Q approach?
the modular ion Q approach. Ah, right. Okay. So I think this is the um, approach where modules with relatively small numbers of qubits are linked together optically and photonically. Is that, do you understand? Is that what you understand, Raghu, by the?
I think that's how I would interpret
Right.
it.
Okay. Well, we spent 5 years building a whole experiment here in Oxford to demonstrate some of the ideas of that modular approach, and we have what's pretty much the most advanced lab experiment in the world for doing that. I think it is going to be very important because I think that just as with our existing computers, networking them together makes them a lot more powerful, right? I mean, the phone in your pocket, smartphone is actually a pretty powerful computer by my standards, certainly compared with anything I remember when I was younger. But it's made incredibly more powerful by having communication and being part of a network and being able to communicate to a server farm or whatever. So I think that will be important, but I don't think it's essential yet at the moment. So I think that there's quite a long way to go where you can build up to quite a large number of qubits on one quantum chip of whatever variety, whether it's superconducting or trapped ions, before one is forced to network them together to make the computer more powerful. I'm guessing there's going to be some sort of maximum number of qubits that one can conveniently manipulate on one chip, and that may not be big enough to make an error-corrected quantum computer. So networking together and networking via photons in this modular approach is very attractive because photons, the natural sort of carriers of information, you can stick them into optical fibers, send them over moderate distances, and photons don't need to be in a very cold environment to be, they kind of carry quantum information quite faithfully, even in room temperature and so on. So I think that will come. I think it's we don't need to focus it perhaps the companies perhaps don't need to focus on it right at this moment.
All right, great, thank you. Another question from Jonathan. In the 1920s and 30s, the important mathematics was operators on Hilbert spaces and representations of symmetry groups. Is there today similar mathematics for quantum entanglement and computing?
Oh, wow, that's a great question. You're asking the wrong person because I'm not a theorist, but well, I'm sort of dimly aware of various things that people on the more mathematical side work on, such as well-known one is the ZX calculus, which is a sort of method for writing quantum algorithms and quantum programs and so on. So I don't, yeah, it's I guess the analogy with the operators and so on. I'm not aware of new mathematics you need because, in a sense, the quantum computer, everything about the quantum computer is contained within quantum mechanics that was invented 100 years ago. So it's all based on that, I guess, conventional quantum mathematics. But as I say, I may just not know enough here. Don't know whether Raghu, you know of anything else that's
No, I'm
on the theory.
not a theorist either.
Yeah.
Okay, so maybe two related questions from Narration Simon. What is your best guess when a commercial quantum computer will be available, and how will their power be compared to classical current computers? And how long until we have a quantum computer with real-world applications?
Okay, well, a question that everyone wants to know the answer to. Well, we do have commercial quantum computers right now, actually, right? You can, there are small quantum chips. I think maybe IBM was the first company to put one up sort of open access on the web, or with, I think their first machine had like 5 qubits, and they have machines with, I don't know, 10, 20, 50 qubits. I don't know. Now, on some of those, you pay for time on. So that is a commercial system. Rather like early days supercomputer, and in the trapped ion world, I believe that Quantinuum does this, IonQ does this as well. These big companies, and so you're using real quantum hardware there. Now the thing is, the catch is, even though these systems maybe have 50 qubits, and by the way, 50 qubits is is quite an important number to get to, because if you had 50 perfect qubits or very well controlled qubits, that's at about the limit of the biggest possible system one can simulate on a classical supercomputer. In other words, a 50 particle system where each particle just has two states. The full, Hilbert quantum mechanical Hilbert space of that requires so many variables to store it. You require a huge supercomputer memory, and 50 qubits is about the kind of turning point there. So there are systems out there with 50 qubits. They're sort of just at the borderline of being able to do things that the biggest classical supercomputers can't do. But I think I'm right in saying that at the moment they can't do anything useful in terms of what you want, which is a useful application. So they can do certain sort of toy problems, which quantum computers happen to be better at than classical computers. But my guess is that definitely within 10 years, maybe even 5 years, systems will be big enough to be doing more useful applications, which they're not, they're going to be breaking codes, I don't think, soon, because that's quite a high bar. You need quite a lot of qubits to do that and to be very well error corrected and so on. But there are many interesting physical systems, like sort of moderate sized molecules, which are difficult to simulate on classical computers, that we ought to be able to simulate better on quantum computers. So I think a bit like conventional computers, they'll have their first applications will be in specialized scientific applications. And I would say, yeah, come back in 10 years. I reckon they'll be here.
All right, great. A question from Bob. Can you say something about Microsoft's Majorana / topological qubits? Is it likely they actually have something?
Sorry, people do. I should know more about them, but I don't. So this is something that seemed like a very interesting theoretical idea, because if I remember rightly, that they would be more intrinsically resistant to noise than a lot of the other qubit systems. But I also think I'm right in saying that they had a sort of paper where they thought they claimed to have discovered these things, and then they had to retract the paper because there was something dubious about it. So seems like they're not there yet. I mean, it doesn't mean I rule out their existence. It's I think it's just a very early stage technology.
And I mean, I think it's probably fair to say that they haven't actually demonstrated the qubit yet, even though they've made a lot of progress in the underlying technology to read out these states, let's say.
Right. Yep. Yep. That's right. So, yeah, demonstrating it. Yeah. Yeah. And there's quite a few. I mean, as I say, I've been working on this sort of stuff for 20 years. So if I go back sort of 10, 20 years, people were very optimistic about silicon qubits. In other words, qubits made in silicon technologies. It took them a long time to get to the point where they really had a single qubit under good control. And now it was in about 2015, they first managed to get two qubits gated together and so on. So it's that's not to say it's not a very promising technology, but it's perhaps 10 years behind the superconducting circuits or ion trap technologies that are working more reliably at the moment.
A question from Wayne. I see that 2 to the n qubits in superposition can test each possible factor, but how does the information encapsulating the right factorization come out of the system?
Yes, that's a very good question, and a subtle one. So that the sort of art of designing a quantum algorithm is such that your quantum register, which will evolve through some very complicated superposition state under the control of the operations that you're doing, which are really these gating operations, and it will evolve to rather than just a sort of even superposition of all possible states, it'll evolve closer and closer to one possible state, which is overwhelming probable compared to all the other terms in the superposition. So if, for example, you're searching for something, so there's a famous algorithm called Grover's search algorithm, which is something that quantum computers can be better at on paper than classical computers, searching through a database for something. Then at the end of this search operation, there'll be one term in that superposition which will be much more probable than the other. So when you measure your qubits, you'll get that answer with high probability. And if you're worried that it might be the wrong answer because it's only a probability, you run the algorithm a few times, and you say, oh, I get the same answer 3 times or 9 times out of 10. That's still faster than doing it on a classical computer, and it gives you confidence this is the right answer. And also, if it's the kind of thing like factorization where it's easy to test if you've got the right answer, you can test whatever answer the computer spits out. So
Right, thank you. Uh, Question from Robert. Outside of the impact to cryptography, what, in your opinion, is going to be the biggest impact, good or bad, of a practical quantum computer on society and our technology?
Well, if one asked that question about classical computers, it would be very difficult to give an answer. So, I think that the initial, as I say, applications will be in what I would say science applications. So maybe that they will be lead us to discover new kinds of molecules that might be useful for, ultimately, I don't know, for medicine or, I mean, Raghu, you had a great example in a talk you gave at Balliol recently about fertilizer and fixing nitrogen, which is something that, the natural world, biology seems to have evolved an incredibly efficient way of doing this, whereas our chemical processes require huge amounts of energy, and so those kind of processes at the molecular level, surely if we understand more about those, it is going to give us more power to invent new materials or new chemicals or whatever. So that's maybe that's a vague sort of thing. I have to say, there's always been a part of me which thinks in the interest of physics and advancing physics. Quantum mechanics has all these mysteries that people are uncomfortable with, but as I say, it seems to pass every test that's thrown at it. I always felt that maybe what you're doing in building a quantum computer, you're going to get into this system where you have incredibly good control over many, many particle entangled state, which is not really something that exists in a general way in nature. So I always had this kind of hope, well, maybe this is pushing into a new regime of physics. Maybe we will discover something new about quantum mechanics, which will shed some light on these sort of mysterious processes of superposition and entanglement. And so that's the kind of fundamental science hope I have, that when you build a bigger particle accelerator and you get to some new energy, you discover new things, right? Because you get into a new regime that yeah, you've never been able to study before in a controlled way. Even if those energies exist in the supernovae or black holes or whatever, that the particle accelerator is much more useful because it enables us to study in a controlled way. Maybe making these large multi-particle entangled states will lead us closer to an understanding of Schrodinger's cat and that paradox.
Right, great. Question here from Tim. A simple example of how data is loaded into an assumed perfect quantum computer and how the result is read out would be nice.
A simple example of how the data is loaded in. Do you say, and how it's read out?
Yep.
Yeah. Okay. So how do we do that in our quantum systems here? So can I go back to? You've still got my slides, Rocco, I guess. Yeah.
Yep, I can see them.
So if we look at our qubit states here, so how do we get information into this qubit? How do we set it to be 0 or 1? So there's a process which we use called optical pumping, which basically means you shine a laser beam onto the atom here, and it could be with a certain polarization of light. And after a few microseconds, the atom will be pumped to one or other of these states. Okay, depending on what polarization of light. So if we use the right polarization, we can ensure that the atom is always in this 0 state. Yeah. Okay, and that might not be the ground state of the system, but for all intents and purposes, it's infinitely long-lived in this isolated atom. It'll just stay there. So that's how we get information in. And well, I guess I should point out that if you've got a whole register of your qubits here, because they're separated here by a few microns, you can, in principle, focus a laser beam down to hit one of these ions individually. Okay, so you take this laser beam, give it the right polarization to prepare one of the states, focus it on the left-hand qubit here, and it will pump it into the 0 or 1 state. And I can move along, fire another laser beam or move my laser beam along, and I could give it the same or the opposite polarization, and I could set the quantum state that way. To read out the system, well, if I had a energy level diagram here, I'll show you that it's rather similar. We can drive transitions in the atom between one of the qubit states here and another third energy level up here. So my laser pointer seems to have disappeared, but I'll get it back in. Right, there we are. Imagine there's another energy level up here. We can drive transitions such that if the qubit is in one state, it responds to that laser beam, absorbs light and scatters light, but comes back where it started, and then it just cycles round and round that transition, fluorescing, and is bright. Whereas if it was in the other qubit state, it stays dark and doesn't fluoresce. So that's how those are the ways we prepare the qubit state at the beginning and the way we measure it at the end of the operation.
Right, great, thank you. Question from Richard. How long before we have quantum computers that render current encryption based on primes redundant?
Yeah, I don't know. I think that's longer than just before kind of useful applications. And it's really a bit of a how long is a piece of string question. I think one can write down, I need, if I can get the precision of control of the qubits up to a, say, 99.99%, and I've got, I don't know how many qubits I need, maybe 1 million qubits at that level to factor a 2048-bit number. I think even then it would take about a year on the sort of systems that we use, minimum, in terms of the number of operations it takes. So it would take a year to factor the number. So, most people aren't going to be prepared to wait around a year when they're trying to break a code. So that's pretty slow progress. And that machine I've just described, that is a very tough engineering challenge to get to that point, to have 1 million qubits with state-of-the-art errors, which have only up till now been demonstrated in, I think, one hero experiment anywhere on the planet. So it's going to come, I'm sure, because if nothing else, there's no law of physics that says we can't do it, right? And therefore, why wouldn't you want to do this? I mean, a quantum computer is the most powerful information processing device that is allowed by the laws of physics. So I think, we're going to build them, but it's going to take perhaps longer than one might like, but it'll probably have an impact that's maybe bigger than we expect at the moment. So, and it's going to be a strong function of how much money is poured into it, of course, into solving the very challenging engineering problems and research problems that are still there.
Great. Maybe a related question from Anna. What are you advocating for the future of keeping, for example, payments secure?
Oh, I'm not advocating anything, but it is the case that quantum mechanics, as well as giving you the ability to break conventional code breaking, also gives you more secure ways of making codes. Okay, so quantum cryptography, actually, which I haven't talked about at all, is a system where we can use individual quantum particles like photons of light in such a way that our friends Alice and Bob can share a secret key, and it is absolutely, in principle, impossible for an eavesdropper to snoop on the key as it's being transmitted in this single photon method without Alice and Bob knowing about it, because there is this property of quantum mechanical systems, which as soon as I measure them, if they're in this superposition state, as soon as I measure them, I will so-called collapse the wave function, but I'll get an answer that's one or the other. I mean, that's exactly what's happening in my entanglement video here. Right, when I'm, as I said, I'm preparing this 00 plus 1 state and then measuring it repeatedly. And although it is in a superposition state until I measure it, as soon as I measure it, it's clearly either bright or dark. So that property gives the ability to exchange secret keys using quantum mechanical particles in a way that is, to the extent we understand quantum mechanics and believe it to be true, impossible for anyone to eavesdrop on. So there are more powerful methods of cryptography already available, and you can go and buy a quantum cryptography system from one of our commercial sponsors, whose name will appear any moment on the screen. Maybe only in the YouTube version of this that Dave Barker says is coming afterwards. Anyway, so you can go buy a commercial box that does quantum cryptography. At the moment, it's less, it's more inconvenient than just using the conventional cryptography method. So I guess that's why it's not wide use. But yeah, if we needed to do that, there are these sort of so-called post-quantum cryptography methods.
Thanks, David. A question from Steve. Any books you can recommend that go into more detail, presumably on quantum and quantum computing?
Yeah, I'm just looking up on my bookshelf here. There's a great one. I can't remember. the title. Oh, wait a minute. This is yeah. There's a couple I remember reading one ago. Ages ago. One is called The Code Book, actually, by Simon Singh, which is more about cryptography, but has a couple of very good chapters on how quantum cryptography works and a little bit about quantum computers. And if you read that, you'll see that most of my talk about cryptography was just stolen straight from Simon Singh's book. So that's a great book. And one that's another one, I don't know whether you can look at it, but called Minds, Machines, and the Multiverse, goes into a bit more detail about quantum computing. That's by a guy called Julian Brown. Minds, Machines, and the Multiverse. So that's another very interesting book. It actually explains, takes you through like a basic quantum algorithm and how it works. That gives you a bit more detail, but it's still written for a layperson. It's not a highly technical book.
I might maybe just add to this The Dance of the Photons by Anton Zeilinger, who won the Nobel Prize like a few years ago. I thought that was quite a nice book for
Yes, thanks,
the
Raghu.
popular audience as well.
Yeah. Actually, Raghu is always recommending interesting books to me, so he should have. You might have other ones, Raghu, that you could come up with.
I mean, that's the main one that came to mind. Maybe one last question from Shobit. What kind of algorithms do you think we still need in quantum computing before it makes these computers viable at scale?
What kind of algorithms are? Well, I suppose a crucial thing when you say viable at scale, I mean, one of the most difficult um, challenges in quantum computing is correcting the errors that one gets on the fundamental qubit operations. So, uh, indeed, for the first sort of 10 years, the theoretical idea of a quantum computer, people thought, well, that's a wonderful idea on paper, but how on earth can you ever build it? Because no physical system is free of errors. And how do I correct the errors in a quantum system? Because I can't measure the system without changing it, collapsing the superposition states. So therefore, I can't measure errors. Therefore, it's going to be impossible to build one. So a big surprise really was the discovery about 10 years in of something called quantum error correction, independently by Peter Shaw, who invented the factorization algorithm, and Andrew Steen, working here at Oxford, discovered how to square that circle, actually, of being able to detect the errors that have occurred and correct them without directly measuring. So that's a whole story in its own right. So, but maybe there are more efficient ways of doing that we haven't discovered yet. So at the moment, error correction, requires, as I say, more qubits and better qubits. So you have to get the qubit operation fidelities to 99.9% or something like that. And then even then you need maybe 10 to 100 actual physical qubits to represent 1 qubit's worth of information, or a logical qubit, as it's called. So it would be great if we could get that ratio down to, only needing, say, 3 qubits to represent 1 qubit. So, if there are clever algorithms for doing the error correction that may come in, or might come in if people make the physical operations more and more reliable, they're maybe more efficient error correction. So that's a kind of algorithm, right, which is just an algorithm that keeps the computer going and operating, and enables you to do your whatever program you want to run.
Right. Maybe one last question from Rag Yadava. So wondering on your thoughts on Federico Fagini's recent work, Irreducible Consciousness, Life, Computers, and Human Nature. If you know that.
Well, unfortunately, I'm not familiar with the work. So, but
Yeah.
it sounds very fascinating. I mean, I do, there've been various people, I think Roger Penrose, for example, is one over the years have speculated that our consciousness may have something deeply to do with quantum mechanical operations and so on. And that is something I guess I'm not qualified to know about. I've never been persuaded yet by the idea on the basis of evidence, but it's a bit like asking, I suppose, if artificial intelligence could ever replicate human intelligence, because AI systems that we have at the moment are definitely not quantum, and yet they can do some things which appear to be, very similar to human intelligence or even human creativity in some aspects. So I'm not sure that quantum effects are essential for intelligence, but maybe they are. So who knows?
Right. Thanks, David. I think maybe this is a good place to stop. You mentioned that you also have a hard stop at 6:30 or so.
Yeah, well,
No,
thanks everyone for coming to the lecture. And thanks Raghu for hosting, and thanks for all the great questions and thought-provoking questions too.
yep, and thank you, David, for the lecture, but also answering the questions. Maybe just one last bit from me on the upcoming lecture. The next one's in September by Professor Sebastian Schummelt on building animal bodies, the mechanisms that regulate animal shape and form. Right. So that's all we have for you today. Thanks again for your attention and all the questions and the lively discussion. And we'll see you for the next seminar in September. Thank you.
Bye everyone.